Well, today we're going to talk about designing JSF applications using the USDP. USDP means Unified Software Development Process. As well as a review of the USDP, we're also going to take a look very briefly at how we can use the designs that come out of the USDP as the major focus of our Java Server Faces applications. As ever, you'll need to remember what you've learned about managed beans, MVC, and the life cycle, also a little bit about navigation rules. A lot of people say, when asked, what process are you going to use for designing your application, they'll say the UML. But the fallacy of that answer is in the name of the UML. It's a language, not a process. Being a language, it's only a set of diagrams that we use to record our decisions as we plan our applications. What they don't do is tell us how we can address the problems that we're trying to solve. Therefore, what we really could do with is some kind of process that will guide us through the problem-solving process. One such process is the USDP, Unified Software Development Process, which makes use of the UML in terms of its diagrams and suggests an order in which those diagrams can be used to get from the initial problem description to the final program solution. The diagrams that we will use from the UML to achieve this are the use case model and attendant activity diagrams, analysis models, class diagrams, and sequence diagrams. And you'll see from the slide here that there is a change of focus. When we're starting off with the use cases and the activity diagrams, we're very much focusing on the problem domain. We should not be thinking about the solution at this point. Now, as developers, it's almost second nature for us to immediately start thinking about what the screens are going to look like, what buttons there are, and when I click this button, it's going to give me this kind of a result. When we're designing, we really need to step back from that instant urge of getting into the code and think about the problem domain. The problem domain is defined by the real-world situation in which that problem finds itself. So if it's a problem about library books, then we go to the library and we look at what we find in a library. And we talk to the librarian, we talk to other people who work in or use the library, and we start to learn about their viewpoint, the user's viewpoint of the problem domain. We also look for the terminology that they use, the language of a librarian, the language of a library user. And we use the language and the context and the entities that they speak about and that they use. That all forms part of the problem domain. And we focus on that problem domain as we're developing use case models and the activity diagrams. That will help us to define what the system is to do. It says absolutely nothing about how. So we start off by answering the question what. The next stage is for us to think a little bit about how, and that's where analysis models come in. We're taking a partial step towards a solution, and we will do that, as we shall see in a few minutes, by starting to think about the kinds of classes that we might want to make use of. Once we've got that established fairly clearly in our minds, then we're ready to start writing the actual solution, and that will involve the class diagram and the sequence diagrams. By then, we are very much in the solution domain. We're thinking about the object-oriented classes. We're thinking about the screens and the buttons and the text fields and all the rest of it. Now, the USDP is a use case-centric process. So all that it does is centered on the use cases. We start off by defining those use cases, and then as we proceed with the development process, we do so by focusing on use cases. The question, what does the user do with the system, forms the basis for identifying the use cases. The USDP is also architecture-centric, so it will focus on the form, the architecture of the system. One of the things that we do during the analysis stage is to think about the architecture of the software, to think about the kinds of classes that we will need at the boundaries and as entities and as managers and so on. And the communication between those architectural components will also be defined. Thereafter, as we build the solution, we will build it according to the architecture that we've come up with during the analysis stage. Now, software architecture has two distinct aspects, static and dynamic. Static is all about structure. It's about the classes that we will have and the relationships between those classes. So we could have class A contains an aggregation of class B. That defines the structure between them. What it doesn't define is how they then communicate. And that's the dynamic part of an application. The communication or behavior will be described, for example, in sequence diagrams. And so it isn't enough just to write some class diagrams, because that only defines the static nature of the application. We also need to identify the dynamic part of it as well. Thirdly, the USDP is iterative and incremental. So it isn't like a waterfall model where you start at the beginning and you do stage one, which is usually the specification stage, and get it all finished before you move on to the next stage. No, it's very much iterative. So you'll do a little bit here and a little bit there. You'll do a bit of specification, a bit of analysis, a bit of design, maybe a bit more specification because your design has led you on to thinking about other things. So you go back to the user and you consult again and you find out a bit more information, and that gives you a bit more specification, a bit more analysis, a bit more design, and so on. So this iterative approach will also lead naturally into being incremental, so that you build a bit at a time. You build a bit of your specification and then your analysis and then your design, and then go back and do a bit more and add some more into it. In terms of implementation, we should find that each increment will also build a stable working system, but a limited one. And this is a very good approach for assignments, because when you come to write your assignment, you might have 12 use cases for your entire assignment. And there's a tendency for students to want to build all 12 of them before they even run it and test it. And that's a pretty dangerous way of proceeding, really, because you will waste so much time debugging. Whereas if you take one use case and implement that one use case, all your debugging will be focused on the things you don't understand properly on one use case, not 12. And you make all your mistakes on that one use case, correct those mistakes and learn a lot. Once you've done all that, then you won't make anything like the same number of mistakes for the remaining 11 use cases. This idea of building a bit and then testing it is a very powerful concept, and you should employ it for your assignment. Let's look a little bit at the diagrams that you'll be using with the USDP. The use case model is a collection of use cases. And an individual use case answers this question: what does the actor, user, want to do with the system? If we word it slightly differently, the actor uses the system to, and whatever comes after the word to is what you write for your use case title. So if the member of the library wants to use the system to borrow a book, then borrow a book is what you write as the use case. The librarian wants to list all members. List all members is a use case title. So it's very easy to identify the names that we're going to give to the use cases. But a use case is very abstract, by which we mean it has almost no detail at all. Borrow a book, 3 words. It conveys a certain amount of information. The more familiar you become with the problem domain, the more information it actually suggests to your mind. But it doesn't really give any detail, just gives you a name, suggesting what might be taking place. And so a use case diagram on its own is no design at all. It gives you nothing on which to build an application. We need to give a lot more detail. And so part of the USDP, part of that process, is to guide us in adding more and more detail until we've got a finished solution. And that's where the other diagrams come in very handy. Here's an example of a use case model. Only 3 use cases. We can see the actor. The actor is named student, and each use case that a student can execute is attached to the actor symbol by an association, a line. So a student can use the system to register for a module. A student can use the system to change a password. The student can use the system to view results. Now, if I were to ask you, how are you going to register for a module? The correct answer is, I don't know, because that information is absent from this diagram. And properly so. That's not the purpose of this diagram. It's very much an overview diagram to show you in one or maybe two or three simple diagrams the functionality of the system and who can perform that functionality. But we might want to add a little bit more information. For example, an include relationship. Sometimes there are several use cases that have some kind of relationship. In this case, an include relationship. And what that shows is a use case that must, note the imperative, must execute another. In this diagram, the actor who is executing use case A must also execute use case B. That's what the include means. So when use case A executes, it must also execute use case B at a time that it decides. And we'll see in the activity diagram that you would then write the use case B at the appropriate stage in the activities that will form use case A. And the other thing to note here is that use case B cannot execute on its own. Here's an example. You might want to ensure that every use case that student can execute will only execute if the student is logged in. And so all three of those use cases will include another use case that will check logged in. And when we look at the activity diagrams, we would expect to see for each of those three use cases a reference to this fourth use case, check logged in. Typically, it'll be right at the beginning of those diagrams. Here's another relationship, extend. This is not an imperative. It is a possibility. It's an option. It shows that a use case might be executed by another. In this diagram, we can see that when use case D executes, it might also execute use case C, because, according to the diagram, use case C extends the functionality of use case D. As we can see from this diagram, we could also execute use case C in isolation. But if we execute use case D, then we have the option also of executing use case C. For example, when a student registers for a module, the student might also register for a co-requisite module. But not all modules have co-requisites, so that bit of functionality will only come into play when the module we're registering for has a defined co-requisite. And for the other modules, the register for co-requisite module will not execute. So it's optional, based on certain rules, conditions. Note, please, the direction of the arrow for extend. It's a little counterintuitive. Register for co-requisite module extends register for module, so which is the one that is the driver of all this? The one that is being pointed at, register for a module. Now, an activity diagram starts to give more detail about a use case. It describes a given use case, and it will represent a flow of activity for that use case that it describes. Again, the focus is on the problem domain. So we are using the vocabulary and our observations of what is happening in the real world to define the activities that should take place within this use case. If ever you start writing something like click submit button, give yourself a really good hard kick in the shin and tell yourself, get back into the problem domain. Clicking a button is part of the solution. It's something that you might decide to put on a graphical user interface, but you might not actually write your solution as a graphical user interface. You might have it as a command line application. So the idea of having a button in a command line application is meaningless. Keep out of the solution, stay in the problem domain. Here's the anatomy of an activity diagram. Note the use case name at the top. That's the label of the diagram. This tells us that this diagram is related to that use case. Remember, the whole process is use case centric, so we're focusing always on the use cases. What follows is a flow of activities that describes the major tasks within the view results use case. This circle indicates the initial node. It tells us where to begin the flow. And we follow the arrows to an activity. So the first activity is check student ID. How? Wrong question at this point. We're still focusing on what. When we're sat in the real world watching a student walk up to the desk to ask the librarian, "Can I borrow this book, please?" the first thing the librarian will do is say, "Can I see your student card?" Why? That's a good question. Why? To verify that the student is registered for borrowing books from this library. So all of that kind of real-world activity that you can observe, those are the kinds of activities that we're wanting to describe in the activity diagram. We certainly don't want things like select student from list on screen, for example. A screen is a solution. This could very well be done as a paper-based implementation. After the activity, in this example, we've got a decision node. Please don't go away with the idea that you can only have one activity before you have a decision node. Every decision node must be preceded by at least one activity, but you might have multiple activities in a sequence before you have a decision, and some use cases will have no decisions at all. But if you have a decision, the decision will come after an activity that tells you what you're doing. So for example, we're going to check the student ID, and then we've got a choice. We can either say this student ID is valid or it is not. And so we show those possible routes through the activity diagram with a decision node. Please note the labels on the arrows that come out of that decision node. They are called guard statements, but in our common developers' parlance, they're conditions, Boolean expressions that will tell us which of those two we will follow. So if the student's ID is valid, then we follow the arrow down into get students results. And the other thing to note here is that every decision node must have a corresponding merge node. So this is an end if we were jumping into the solution, which I've told you we shouldn't do. But that's really what we're talking about here. It's the equivalent of end if. If you make a decision, then you're splitting your paths through the activity diagram, and those paths must reunite, merge at some point. It may be that after the merge there will be some more activities, maybe another decision, and so on. Eventually we'll get to the point where we say that's the end of the activity, and the final node is illustrated as a pair of concentric circles, and that tells us that we stop the activity. The use case is now fully described in terms of its activities. I've already mentioned this. Let's just very quickly re-emphasize. The use case models and the activity diagrams are describing the problem domain, not the solution domain. We're using the customer's language and we're giving an external view, a user's view of the system. We're not focusing on the developer's viewpoint. To get to the developer's viewpoint, we need to get into the analysis models. And there we start to describe the solution domain. We begin to use the developer's language. We start to talk about classes and other such things. And we're beginning to think about the internal representation of the system that we're going to build. It's really an intermediate step towards the final solution, but it is an important intermediate step. Now, in an analysis model, we have got these three stereotypical analysis classes: boundary, control, and entity. A boundary analysis class is a circle with that T on the side, and an actor can only interact with a boundary class. That's why it's called a boundary class, because it sits at the boundary of the system and is the point of reference for an actor. The actor will send its requests to that boundary class and will get responses from that boundary class. Right at the other end of things, data is stored in entity classes. So these will be objects that store data and will have behavior as well. Those data will persist in the system. So it's things that we're interested in keeping a record of. In a library, books, members. In a university, students, modules, results, and so on. Between the boundary and the entity, we will very often find these control classes, sometimes called managers or handlers. Their job is to coordinate complex operations between objects or to manage the entities. We might, for example, want to create a module. Well, the message will come in from the actor to the boundary class to say, I want to create a module called Java for Beginners. That boundary class will send a message to a controller to say, look, here's the information I've got from the user. Now use this information to create a module entity for me. So the control class is going to manage collections of entity classes. Just to re-emphasize the first point on the slide here, please remember the USDP is use case centric. Therefore, there will be an analysis model for each use case. Here's an example. The use case is view results. Therefore, we show the actor that is associated with this use case sending a message called view results. That's the name of the use case. We give it a number to say this is the first message in the sequence of messages on this model. And you can see that that goes into the boundary class, and the boundary class is given a name, something meaningful. Student UI, for example, to say this is the student user interface class. Now please remember that these are stereotypical classes. They are for analysis purposes. It's really just to suggest the fact that there will be, in the final solution, at least one class that will form the user interface. How we actually implement that, well, that's a decision for a little bit later, but how we implement it will depend on some decisions such as what kind of application am I going to write. Let's say we're going to write a desktop application with Windows. And if we're doing that in Java, then that one class will involve a JFrame, at least one JPanel, layout manager, buttons, text fields, and so on. Lots and lots of different classes. But that's a decision for later. For now, on the analysis model, we're adding a bit more detail, but not lots. So we just represent that one user interface concept with one boundary class. Typically, we'll find that for each actor, there will be one analysis class for the boundary. So a student UI, librarian UI, lecturer UI, and so on. Now the student UI has been sent the message, view results. So it must now coordinate the response to that request. Well, to view results, it's going to need to get hold of the student for whom these results have been requested. Now there's a collection of students, almost certainly, in your system. It might be in a database, or it might be held in memory, or it might be in a file somewhere. Again, that's an implementation decision. We don't care about that just yet. All we know is that there will be a collection of these student entities somewhere. And rather than have the user interface class just try and search through all of the records, let's separate responsibilities and have this control analysis class called student manager do the searching for us. It's going to manage that collection of student entities for us. So the student UI class can send a message to the student manager class saying find student. Implied in that message there's going to be a student ID. We don't show that here. That's a decision for the final solution when we come to do the class diagram. For now, we just show the bare bones of it, which is the name of the message. View results inevitably is going to need a student ID, especially when we think about the activity diagram that we were viewing a few moments ago, where the first activity for that use case was check student ID. What student ID? Well, we can deduce that the student ID will arrive as part of that message, view results. And then we'll take that student ID and pass it on to the student manager as part of the message, find student. But that's just deductions that we make because we're developers. That detail will be added later once we finish thinking about the high-level solution, which is the analysis model. Now that manager will find the student and return a reference to the student UI boundary class. And that means the student UI boundary class now knows where that student is and can send a message to that student entity saying something like get module results. And then it will display those results. But again, we don't need to show that. That's solution. That will come later. What we're focusing on with the analysis model are the types of classes that we will need for a given use case, the names of those classes, and the messages that will be sent between those classes. When we come to the class diagram, this is where we really get into the detail of the solution. We've thought about the kinds of classes that we want in the analysis model. Let's just go back to that analysis model for the moment. We need a student UI class, a student manager class, and a student class. And we can see all of those in this class diagram. Student UI, student manager, and student. If we go back again, we can see that there is a message to the student UI class called view results. In the class diagram, that becomes a method in the student UI class. The name of the message becomes the name of the method, showing very clearly the linkage in our thinking from analysis to design. And that will happen with student manager as well. Student manager receives a message find student, and so in the student manager class there's a method called find student. And here is where we put the details such as parameters and return types. We also understand that the student manager's job is to manage a collection of students. And so in this class we've got an attribute called students of type student array or student collection. And we'll see the relationship between student manager and student as an aggregation. Since the student UI class needs to send a message to the student manager class, it means that the UI class has got to have a reference to the manager class. And so there is an association, unidirectional association, set up. And again, that is reflected in the attributes for the UI class. Remember, this represents just a single use case. If you've got 10 or 12 or 1,000 use cases, you will have 10 or 12 or 1,000 analysis models. Now, when we think about view results for a student and register for a module, there are going to be some overlaps. They're both going to use the student UI boundary class. They're both going to have a student manager control class. One will have a student entity. The other will also have a student entity and probably a module entity. So we'll find there's a lot of overlap. As we build the class diagram iteratively and incrementally, use case by use case, we will find that we will use the same classes but for different purposes. Different messages will be sent to them. Therefore, we'll start to build up a list of methods. And by the time you've finished moving the analysis models into the class diagram, you'll have a fairly detailed class diagram. But that's not the end. That's only the static part of the solution, the structural part. We've got to describe the dynamic part as well. And that's where the sequence diagrams come in. This is a snapshot, an imagined snapshot of what might happen at runtime. When view results message comes in from the user to that boundary class in the analysis model, that in the final solution is going to be a method call to the UI class or an object of the UI class. So we're now showing the methods and the objects of those classes. View results comes to an object of student UI. That method is going to call find student in student manager. You see that we're now mirroring what's been decided in the analysis model, and we're also implementing the activity diagram sequence of activities. So when we're building this diagram, we will refer back to the class diagram and to the activity diagram, because the activity diagram gives us the sequence of the messaging, and the analysis model has given us the message and therefore the methods in the classes. And this is the final part of our solution, because it tells us that when view results happens, first we call find student in the student manager, then we're going to call get module results in student, and then we're going to call get module from the student module collection, and then get code from module, get title from module, and get result from student module. Now that will only make sense after we've decided on what the class diagram structure will be, what classes we've got. So you can't do this any earlier. but it is an important stage, because without that, if you were to give your class diagram to another developer to build your program for you, they would not have the right information without this sequence diagram. So all 5 of those diagrams are really important. Use cases, activity diagrams, analysis models, class diagrams, and sequence diagrams. There will be one use case diagram. For each use case, there will be an activity diagram and an analysis model. There will be one class diagram, and then again for each use case, there will be a sequence diagram. So if you've got 12 use cases, that's going to be one use case model, 12 activity models, 12 analysis models, one class diagram, and 12 sequence diagrams. That's quite a lot of diagrams. So when it comes to the assignment, don't leave it till the last minute. With that overview of the USDP, we're now ready to start thinking a little bit about how this fits into JSF. Because with JSF, we've got views and managed beans, and then some POJOs that the managed beans can interact with, and probably a database. How does all that fit in to a USDP design? Well, the first thing to realize is that a USDP design, like any good design, could be implemented in a whole host of different ways. You could build it as a command line application, or a graphical user interface application, or a web application, or all kinds of other applications. You could write it in Java, or C++, or Visual Basic, or anything else. The one design should give rise to any of those implementations, at least up until the analysis model. Once you start building the class diagram, that is when you are making final decisions about your implementation. So if you've decided that you're going to have a graphical user interface, it's in the class diagram that we'll start to see that the boundary class devolves into JFrames and JPanels and JText fields and so on. What we've got to do now is to adapt our diagram to a Java Server Faces application. So we need to think about what managed beans we're going to have and how the other classes fit. For me, I think there are 2 fairly straightforward ways to make a USDP design applicable to JSF. The first is just to take the UI classes and convert them into the managed beans. So in your USDP design, you've got your boundary class with all those methods coming in. Those effectively will become action methods that the views will call when the submit button on that view is clicked. So the managed bean becomes the interface class. But that means you're going to have to add in a whole load of other things like properties, the fields and the set and get methods. So in a way, you've kind of lost the purity of your original design because you've had to add in extra methods and variables to make the managed bean work with the views that you want it to work with. So for me, a better approach is to create JSF managed beans like we've done so far and have the beans that sit behind the views that we want, and then have those beans in their action methods call the UI classes from the USDP design. So those UI classes are essentially POJOs that sit behind the managed beans, and the managed beans interact with those UI classes. For me, that's a better solution, and we can talk about what that really means in the tutorial. By the time you've finished the work for this learning block, you should be able to describe all 5 diagram types that we use when following the USDP and list the order in which they are employed through that process. And you should be able to describe more than just regurgitating what was on the previous slide. You should be able to describe with a fair bit of confidence the way in which a USDP design can be implemented as a JSF application.